Dear friends, as promised, I have come up with the third proof of Pythagoras theorem. I have named this as Acharya's method number 3. So as before, for discussion, I have mentioned the email address. You are free to discuss and send your comments. So today's proof is an interesting proof. Here on the left, I have again drawn the right angle triangle ABC with sides small a, small b and small c. And today's proof starts with one basic rule of triangle formation. For this triangle, a plus b greater than c, which is also valid for any other triangle, may not be a right angle triangle. So triangle doesn't form when a plus b equal to c. I repeat, when a plus b equal to c, triangle doesn't form. Or in such a case, the area of a triangle becomes 0. And this is true for any c. So just imagine there is a line C which is the base of a triangle, and two other sides A and B are falling on the base C, and there is no triangle formed, and area of such triangle becomes 0. So using the notation of calculus, I can write d delta, which is the area of any triangle, against dc equal to 0 when c equal to a plus b. So c equal to a plus b is the precondition for triangle area or its change to become 0. So differentiating both sides of equation 1, I get dc equal to dA plus dB, which I show as equation 2. And we make a small observation that when delta or the area of a triangle equal to 0, in such a case, this is the minimum area of a triangle which is possible. So this is also a minimization condition of a triangle of side A, B and C, which is shown in equation 2. So out of 3 slides, I have completed 1, and I go to slide number 2 for further explanation. So now we go back to the normal area of a right angle triangle, which is AB by 2. Variable C is also involved, but C is related to A and B. That's why it doesn't figure in the area equation, which is AB by 2. So we differentiate the equation delta equal to AB by 2 like d delta equal to half ADB plus BDA. And to get the minimum area of a right angle of such area AB by 2, I apply the minimization condition. So it must be d delta equal to 0. That means ADB plus BDA equal to 0, which is as good as saying the same thing in differential calculus. So now we make an important conclusion that right angle triangle area minimization condition, as shown in equation 3, must be or can be correlated with the precondition shown in slide 1, as they involve the same variables A, B and C. So from equation 2 and 3 we can write I will not read out. It's like that: a dc minus dA plus b dA, and slowly we move on to the later steps and do the integration on both sides of the equation, and out of that we get a constant of integration k. And since we know the precondition when b equal to 0, c equal to a for the right angle triangle, we get the constant of integration as a square by 2. And now we'll put the constant of integration a square by 2 back to the previous equation and form the final equation on slide 3. So putting back the value of k, we find the equation as AC plus BA equal to A square. As a reminder, equation 4 has been built up by equating area minimization condition C equal to A plus B. So we can simplify equation 5 by appropriately replacing the value of A, and we get that C into A plus B equal to A square plus B square. Again substituting, knowing that A plus B equal to C, the minimization condition of area, we find the final objective as C square equal to A square plus B square, which is the Pythagorean theorem. So again, the Pythagorean theorem has been proved through this unique approach of area of a triangle, area of any triangle, area of a right angle, and the area minimization condition. Hope you found the proof very exciting. Please contact me, like the video, subscribe, or contact me in the email address. Thank you very much for watching. Good night.